What is pumice? Pumice is a type of igneous volcanic rock that forms when lava, rich in gases, cools and solidifies very rapidly after a volcanic eruption. Because the lava contains a lot of dissolved gases such as water vapor, carbon dioxide, and sulfur dioxide, these gases escape as bubbles while the molten rock cools. As a result, pumice develops a frothy, sponge-like texture full of tiny holes, called vesicles. These vesicles are actually the spaces where the gas bubbles were trapped before the lava hardened. Pumice is light in color, usually white, gray, or light brown, and is so full of air pockets that it often floats on water. It is mainly composed of volcanic glass and minerals such as feldspar, quartz, and biotite, depending on the composition of the magma from which it formed. Most pumice originates from rhyolitic or dacitic lava, which is rich in silica and therefore more viscous, trapping gases more effectively. Because of its abrasive texture and low density, pumice has many practical uses. It is widely used as an abrasive material in products like polishing powders, soaps, and exfoliating scrubs. In the construction industry, it is used to make lightweight concrete blocks and insulating materials. In horticulture, pumice improves soil aeration and drainage, making it ideal for growing plants such as succulents and cacti. Geologically, pumice is an important indicator of explosive volcanic activity. Its presence in sedimentary layers can help scientists identify past eruptions and study volcanic history. Overall, pumice is a fascinating rock that illustrates the power of volcanic processes and finds valuable applications in both industry and everyday life. How is pumice formed? Pumice is formed during explosive volcanic eruptions when gas-rich lava is ejected into the atmosphere and cools very rapidly. The process begins deep within the Earth's crust, where magma, molten rock containing dissolved gases, starts to rise toward the surface. As the pressure decreases during this ascent, the gases dissolved in the magma, mainly water vapor, carbon dioxide, and sulfur compounds, begin to expand and form bubbles, much like carbon dioxide escaping when a soda bottle is opened. When this foamy, gas-charged magma reaches the surface and erupts violently, it is suddenly exposed to much lower pressure and cooler temperatures. This sudden rapid depressurization and cooling causes the gases to expand even more, creating thousands of small gas bubbles within the molten material. At the same time, the magma solidifies almost instantly into volcanic glass before the bubbles can escape. The trapped gas pockets remain inside, giving pumice its distinctive porous, sponge-like structure. The key factor in pumice formation is the composition of the magma. Most pumice forms from high silica magmas, such as rhyolite or dacite, which are thick, viscous, and trap gases more effectively. Because of this, eruptions that produce pumice are typically explosive rather than gentle lava flows. The rapid cooling can occur in several environments: during airborne eruptions, when the material cools while falling through the air, or when the lava enters water, instantly chilling and solidifying the rock. After the eruption, pumice fragments can fall back onto the ground as ash and tephra deposits, or they can float across lakes and oceans for long distances because of their low density. Over time, these deposits may form thick layers that geologists can study to understand the magnitude and timing of past volcanic events. In summary, pumice forms through a combination of gas expansion, rapid cooling, and solidification of silica-rich lava during violent volcanic eruptions. The process captures a moment of extreme volcanic activity, preserving in stone the frozen foam of molten rock, a vivid example of nature's power and speed. How to identify pumice in the field? Identifying pumice in the field is relatively easy once you know what to look for. It has a very distinctive appearance, texture, and feel that set it apart from other volcanic rocks. Geologists and rock enthusiasts often rely on several physical characteristics, field tests, and context clues to recognize pumice in nature. 1. Observe the color and appearance. Pumice is usually light in color, ranging from white and pale gray to light brown or cream. Occasionally, it can be slightly pink or yellowish depending on the mineral content and oxidation state of the lava. Unlike darker volcanic rocks such as basalt or andesite, pumice appears bright and frothy, sometimes resembling hardened foam or a sponge. Its surface often looks rough and porous, with countless small holes or cavities, called vesicles, formed by trapped gas bubbles. 2. Examine the texture. The texture is the most obvious clue. Pumice feels very rough and abrasive to the touch. When you hold it, you'll notice it is extremely lightweight for its size, so much so that larger pieces can float on water due to the air trapped in its vesicles. This low density is one of the easiest ways to distinguish pumice from similar rocks like scoria. Another texture-related feature is that pumice is often glass-like and brittle. If you break a small piece, the edges are sharp, and the broken surface may sparkle slightly due to its glassy nature. This glassiness occurs because pumice cools so rapidly that the molten material doesn't have time to form large mineral crystals. 3. Compare with similar rocks, scoria versus pumice. In the field, pumice is sometimes confused with scoria, another vesicular volcanic rock. However, there are key differences. Pumice is light in color, low in density, and often floats on water. Scoria is dark, reddish-brown or black, denser, and sinks in water. This difference comes from their silica content. Pumice forms from high silica, felsic, magma, while scoria forms from low silica, mafic, magma. 4. Perform simple field tests. Several quick field tests can confirm your identification. Float test: place the rock in water. True pumice will float for a while, although it may eventually become waterlogged and sink after long exposure. Hardness test: pumice is relatively soft, usually around 6 on the Mohs scale, and can often be scratched by a steel nail or knife. Streak test: rubbing pumice on a streak plate leaves a white or light-colored streak, consistent with its composition. 5. Consider the geological setting. Context is crucial. Pumice is always associated with volcanic environments, particularly areas that have experienced explosive eruptions. You might find it near volcanic cones or calderas, mixed with ash and tuff deposits, in riverbeds or along lake shores near volcanoes, in ancient pyroclastic flow deposits. Finding pumice in such areas supports your identification, as it indicates a volcanic origin. 6. Look for secondary evidence. Pumice often occurs with other volcanic materials such as ash, obsidian, and tuff. If these materials are present in the same area, it strengthens the likelihood that you're dealing with pumice-bearing deposits. Over time, pumice can also become compacted or cemented into a rock called pumice tuff, which retains the porous texture but appears more solid and layered. In summary, to identify pumice in the field, pay attention to its light color, porous and frothy texture, low density, and volcanic setting. A simple float test, combined with visual inspection, is often enough to confirm it. Holding a piece of pumice in your hand is a remarkable experience. It feels like a rock made of hardened foam, a frozen snapshot of a volcanic explosion that once hurled molten material high into the air. Characteristics of pumice. Pumice is a unique and fascinating volcanic rock with a combination of physical and chemical characteristics that make it easily recognizable and highly useful. It forms when gas-rich lava cools and solidifies rapidly during explosive volcanic eruptions, trapping numerous gas bubbles within a glassy framework. Because of its special formation process, pumice displays several distinctive characteristics that set it apart from other igneous rocks. Below is a detailed description of its key features. 1. Texture. The most striking characteristic of pumice is its extremely porous texture. It contains countless tiny holes or cavities called vesicles, which are the remnants of gas bubbles trapped during the rapid cooling of molten lava. These vesicles can be round, elongated, or irregular in shape, and they often make up 50 to 90% of the rock's volume. The rock feels rough and abrasive to the touch, and because the molten material cooled so quickly, pumice is largely glassy, meaning that it lacks visible mineral crystals. Its texture is often described as frothy, spongy, or foamy. 2. Color. Pumice is generally light-colored, ranging from white, cream, and light gray to pale yellow or light brown. This coloration is mainly due to its high silica content and the lack of dark-colored minerals. In rare cases, pumice can appear pinkish or slightly bluish-gray depending on the chemical composition of the lava and the oxidation state of the minerals. The bright color distinguishes it easily from darker volcanic rocks like basalt or scoria. 3. Density and weight. One of the most remarkable properties of pumice is its low density. Because it is filled with air spaces, it is so lightweight that many pieces can float on water. This ability to float is a direct result of the rock's high porosity and low specific gravity, which is typically less than 1.0. Pumice is among the lightest solid rocks on Earth, and even large pieces can be easily lifted with one hand. Over time, however, when water fills its pores, pumice may eventually sink. 4. Composition. Chemically, pumice is a felsic volcanic rock, meaning it forms from silica-rich, CO2, magma. It is composed primarily of volcanic glass with small amounts of feldspar, quartz, biotite, hornblende, and other silicate minerals. Because the magma cools so fast, crystals do not have time to grow, resulting in a rock that is mostly amorphous, non-crystalline. The silica content of pumice is usually high, between 60% and 75%, depending on whether it formed from rhyolitic, dacitic, or andesitic lava. 5. Hardness and durability. On the Mohs hardness scale, pumice generally ranks around 6, which means it is relatively hard, but its fragile and porous structure makes it brittle. It breaks easily when struck and produces sharp, glassy fragments. Despite its brittleness, it is durable enough to be used as an abrasive material in industrial and cosmetic applications, such as in polishing compounds or exfoliating scrubs. 6. Structure and vesicularity. The vesicular structure of pumice varies depending on the intensity of the eruption and the viscosity of the lava. Some pumice has uniform, small pores, while others contain large, irregular cavities. These vesicles are often interconnected, allowing water or air to pass through them. The high degree of vesicularity gives pumice a large surface area, which makes it especially useful in applications such as soil conditioning and filtration. 7. Origin and formation environment. Pumice always forms in volcanic settings during explosive eruptions. It is typically found in areas associated with rhyolitic or dacitic magma, where gases cannot escape easily due to the magma's high viscosity. The result is a violent eruption that ejects frothy magma fragments into the air. As they cool rapidly, they form pumice, which may later settle as tephra deposits or float across bodies of water. 8. Optical and other physical properties. Under the microscope, pumice often appears as a mass of glass shards and bubble walls. It has a vitreous, glassy, luster, especially on freshly broken surfaces. Because of its composition, it is non-reactive and chemically stable, and it does not dissolve easily in water. Pumice is also insulating, meaning it can trap heat and sound, which is why it is sometimes used in lightweight insulating concrete. 9. Comparison with similar rocks. Pumice is often compared to scoria, another vesicular volcanic rock, but they differ in key ways. Pumice is light-colored, low-density, and can float on water. Scoria is dark-colored, usually black or red, denser, and sinks in water. This difference comes mainly from the silica content. Pumice forms from felsic, silica-rich, magma, while scoria forms from mafic, silica-poor, magma. 10. Uses and importance. The characteristics of pumice make it valuable in many fields. In construction, it is used to produce lightweight concrete blocks. In cosmetics and personal care, it serves as a gentle abrasive in soaps and exfoliating creams. In horticulture, pumice improves soil aeration and drainage. In industry, it is used as a polishing and cleaning agent. These applications are all made possible because of its low density, abrasive surface, and porous texture. In summary, pumice is a light, porous, glassy volcanic rock with a high silica content, formed during explosive eruptions. Its defining characteristics include a frothy texture, light color, low density, and high porosity. It is both geologically significant, as evidence of explosive volcanism, and industrially valuable due to its unique combination of lightness, abrasiveness, and insulation properties. In essence, pumice is nature's perfect example of how extreme volcanic energy can produce a rock that is both delicate in appearance and incredibly useful in human life.